Hi, everybody. Thank you very much to the organizers. It's exciting to have the opportunity to come and talk in this venue and make some new connections. So I take it that my job today is to give you the programming language perspective on things that you all know very well. As a PL person, I come to this area more or less as an outsider with very different background in terms of algorithmic techniques and underlying mathematics compared to what I use in my day-to-day life. But I do recognize one thing. There are a lot of programs here, and there are a lot of proofs about those programs. And there's a lot of common structure to those proofs. And as a programming language person, the question that I then want to ask is, how much of that can I automate? So that will be the kind of organizing theme for everything that I'll say today. Let me illustrate what I'm talking about with a little story. In the Middle Ages, written communication was the sole province of a handful of experts. Writing was hard. Every instance of a document had to be laboriously copied out by hand. Let's look a little more closely at what this man is writing, though. So he has just finished writing out a proof that his favorite query is differentially private. But you can see that the expression on his face is a little grim. And the reason is that he knows that tomorrow his boss is going to suggest a slight variation of the query that he's just written a proof about. And he's going to have to go all the way back to the beginning and write a new proof for the new, slightly different query and copy it all out by hand. Moreover, he's not the only person that's unhappy in this story. This is a picture of the owner of the database that this query is going to be presented to. And she's angry because she has just spent all day checking this poor monk's previous proof and convincing herself that it is actually safe to run his query against her database. And now she's just been told that tomorrow she's going to get another proof for another very similar query, but she's still going to have to check all of the details because her database is very important. And it's not just that. Besides this query and this monk, there are stacks and stacks of other queries from other monks that she's getting from all directions, and she has to check every last one of them and verify that their proof is correct. So clearly we've got a fundamental scaling problem here. This is not a good situation. We need to do something to help all these people not to have to work so hard to write their queries, and especially not to have to work so hard to check the proofs that the queries are differentially private, because it's the poor person in the middle that is really the bottleneck here, the point where things squeeze. Please.
Isn't the differential pricing property of the algorithm, though, and not the query?
When I say query, what I mean is a program, okay, which is going to be presented and, okay, so good. The system view that I have in mind is that the querier owns the database and is also the only one that's willing to run programs against the database, because otherwise how would you run a program against the database? You'd have to give the program to, you'd have to give the database to somebody else who was going to run the program. That's exactly what we don't want to do. So the picture that I have in mind is that the database owner is very jealous and doesn't want to hand out anything except answers to queries which have been proved to her satisfaction to be differentially private. And so when I say query, I mean the whole program, not just a particular instance of some class of queries, which would be more the case in some of the talks that we've heard already. Okay, so there are a lot of queries or programs coming at this person in the middle. Each one of them comes with a proof that she has to check, and we want to lighten her burden. And also, if possible, we'd like to lighten the burden of the poor monks that are producing all of these proofs and writing them out. So this is the game that we're playing. When you phrase the game that way, of course, it's clear that this is a job for some automation, namely for programming languages. So this is exactly what programming languages are good at or should be good at. So what programming language people like to do is to take situations where ideas are being expressed in an ad hoc way, perhaps very productively, and find the organizing principles so that things can be automated. So in this setting, what we'd like is to provide tools for expressing queries, for expressing differentially private programs, so that the privacy of those programs can be mechanically verified. And we're going to throw at this the whole arsenal of tools from the programming language toolbox, in particular compositionality, building bigger things with good properties out of smaller things with good properties, but also designing small languages for particular purposes, equipping our languages with type systems that statically, if conservatively, give us automated proofs of properties that we care about, and automatic proof checkers, which less automatically but more flexibly allow us to mechanically check proofs of properties that we're claiming. And the kind of picture of the territory that I'm going to cover at a high level looks like this. So there's been a lot of work in related topics. And the path that I'm going to take through it is to consider first work on dynamic tracking of the privacy impact of programs that are running, which historically was the first sort of technique to be tried, in particular in the Pink language. It is a rather lightweight technique. It gives you some benefit, not all of the benefits of some of the other techniques that I'm going to show, but it's very little work and it's quite flexible. I'll talk about Pink in detail, and then I'll talk about another system called Arabat that operates in a slightly different domain. Then I'll move on to static analysis, and I'll tell you about a programming language called Fuzz that's been developed in my group, where, again, the aim is to put little work on the programmer to do most things automatically, but to get higher benefit by using a static type system, and what you pay for that is some flexibility. And then, kind of continuing on, I'll talk at the end about the use of machine automation, machine assistance in proof checking, not where the proofs are not generated by type checkers or by runtime analysis, but are kind of arbitrary mathematical objects which have been phrased in a language that can be automatically verified. And here the kind of trade-offs are, this is lots of work, it's not very much work on the proof checker, so it's good for the person in the middle. It's much more work for the monks on the outside, but you can achieve a very high degree of flexibility. Okay, so that's the kind of territory I'm going to cover. At the end, I'll talk briefly, if there's time, about some other work in programming languages, and more broadly about some other work going on in the systems domain. You can already tell this is a lot of ground that I'm going to try to cover. I don't really care if I get through all of it, but I wanted to try to be as comprehensive as I could in the slides, so that if you're interested, you can go back and look at the slide deck later. Any questions? If you have questions at any point in the talk, I hope you will immediately ask them, because I'm aware here that I'm speaking to a different sort of audience than I normally talk to. So probably I will say things that are obvious to me and won't make any sense to you, or you'll have questions that I don't answer about things that I do say that are obvious. And I hope you'll just go ahead and ask them. I don't really care how much of the talk I get through. I would rather have a good conversation about the beginning of it than breeze through the whole thing with no discussion. So let's begin with the dynamic tracking part of the territory, and in particular with this system called Pink, which I think probably everybody in the room has heard of. But I wonder, actually, let me take a quick poll. how many people feel they're actually familiar with pink in the sense that they could describe some of how it works to somebody that didn't understand? So, okay, maybe the hands are going up and down. So maybe a third, I'm going to guess. So I will go through this in some detail and hopefully raise questions. So pink is a system due to Frank McSherry. And it stands for Privacy Integrated Queries, and it's a pun on the system that it's built on, which is LINQ, which is Language Integrated Queries. So LINQ, the idea is we want to program with databases in some mainstream industrial strength programming language, in this case C#. The bad way to do that is to cons up strings and hand them to the database query processor, and we all know why that's wrong. A better way is to integrate the query language of the database into the programming language, so that words like select, where, etc., become full-blown parts of the programming language, can be checked by static analyzers, etc., etc., can be optimized along with the rest of the program and so on. So, and avoiding kind of a separate language that you have to learn to use the database as opposed to just programming in your language of choice. So what pink adds to LINQ is a layer of differential privacy where essentially the API that you're programming against looks almost like LINQ, so you think that you're posing essentially database queries against structured objects, but where the aggregation commands that you eventually pose against whatever database you've calculated are noised to an appropriate degree, and something is automatically checking that the privacy budget that you've assigned is not violated, and so on. So in a little bit more detail, here's an example of how you would write a pink program. So you take your private data, that's the stuff in ... and that can be anything. So that's your database. And this is the only place in your program where you're actually going to mention your real database. So the rest of the program has to access your database through this variable called data, which is an object of type pinQueryable, which you can think of as a database with a guardian wrapped around it that is protecting access to it. Now, from that database, we can calculate other databases. So for example, the second bit there, we're calculating a new database, a new pinQueryable object, by running a query against the original database that well, in this case, it says search for, okay, so records are the things in the, are the items in the database, and query, sorry for yet a third use of the word query in this talk. So query is some string from this record in the database, and we're comparing it against some other string that we got from the outside. So we're finding all of the records in the database that where some field matches some other string that we got from the command line, and we're grouping it by IP address. So we're finding for all of the IP addresses that made a certain query, in the sense of web query, how many there are. And then the key point is on the last line, where we take this new pinQueryable, this derived thing that we got from the database by doing some database calculation on it. This count operation is returning us a noisy, appropriately Laplace noised version of the actual count. And it's at that point where the privacy budget is checked and so on. So the 0.1 is the scaling factor for the noise that we're adding. And the new pinQuery, the derived pinQueryable, knows how to propagate the impact of that noisy count on the privacy budget of the original database back to the wrapper object of the original database. Okay. So I've kind of told you most of this story already. So each data source is wrapped in one of these pin queryables, which mediates access to the underlying data, remembers how much of the originally specified privacy budget is left, deducts from that budget whenever something happens to the data that releases information, and denies access once the budget is exhausted. So the key insight here is that transforming one database to another doesn't actually release information out of the database. It's still packaged, it's still wrapped in a pin queryable. It's only when you do an aggregation that, that information is actually released, and you need noise. So there are several of these aggregation methods on pin queryables. And so, for example, noisy count was the one that we saw. And there are others. There's noisy sum, noisy average, and a few others, but a small fixed set built into the framework. Okay, now the other interesting part is these transformations, because each transformation needs to map one of these pin queryable objects into one or more new pin queryable objects, which, when they are later aggregated, know how to map the impact on the privacy of the original database back to its wrapper, perhaps appropriately scaled if the transformation on the database is not a one-sensitive thing, but an R-sensitive thing.
What do you mean by the sensitivity of the transformation on the database?
So, for example, the select transformation is just takes individual records and maps them to transformed individual records, so the sensitivity of that is 1. But the group by... sorry? Ah, okay, thank you. Yeah, yes, that's true. So some other transformations, like group by, have sensitivity 2. So a change of size 1 record in the original database could yield changes in 2 records in the derived database. So you would have to scale the privacy impact as you propagate it back. Okay. There are several transformations, kind of all the things you would expect to do with databases in SQL or your favorite database language, with some restrictions. So the main thing that we have to be careful about, as you might expect, is join. Because join is the main operator in databases that explodes the size of things. There are different ways of dealing with that, and what Pink does is it does the join, which explodes the size, but then it does a group so that the sensitivity is in fact always going to be at most 1. A different way of doing it is to say you can only join on a primary key, so that you're joining on a column where each table only has at most 1 copy of a particular value in that column. And that has the same effect. Okay, so we have where, which selects a subset of the rows. We have group by, which we talked about. We have select, which we talked about. Join, we just talked about. And then partition is the last one, which says take the database and some way of partitioning it and produce a whole bunch of databases according to that partitioning split. So you give a set of values that you'd like to partition the database along, and it gives you back a new database, one for each of those values. What it doesn't do is tell you whether the values that you tried to partition on were actually in the database. If they weren't, you'll just get back an empty database for that slot of the partition. And it should be obvious why that's the right thing to do. Okay, so those are the transformation operations in Pink. So, unless there are questions, that's my summary of Pink. And the advantages of the Pink approach are that it's quite simple to implement. The whole implementation of Pink is about 1,000 lines of C# code. It's quite easy to explain to programmers because it's, with very small exceptions, programming using Pink is very much like programming using LINQ, which C# programmers are widely familiar with. And the kind of computational guts of the queries, like the predicates that you use to select rows, are arbitrary C# code. However, there are some limitations. In particular, the one that I want to focus on, because that's the one that's going to be addressed by the static checking approaches that I'll introduce in a little bit, is that the dynamicity of the approach means that you only find out at the end if you've used too much privacy. So if you have a long-running computation, for example, that's going to make many interactions with the database, each of which is going to cost some of its privacy budget, and you find out only after you've done all of those interactions that, or almost all of those interactions, that you didn't actually have enough privacy budget, you've still burned your database. Okay, so it's a little unfortunate that you can't, at the beginning, look at your program and analyze it and say, the privacy impact of running this whole program from beginning to end is going to be such and such. That's less than what's left for the database, so let's not do it at all. Okay, so I think this is the main limitation that Pink has. Aside from the fact that, aside from the limitation which it shares with all of the other kind of pure programming language approaches, that it embodies a particular set of primitives, and those are the ones that you get to use. That set is extensible, so if you have a new transformation that you have proved on paper is differentially private, you can add a new method to the Pink queryable class and use your transformation. But you don't get to program it in Pink. You have to add it to Pink. So for some applications where you have just one new algorithm that you want to add in, and you just do that, and then you're happy for the rest of your programming life, this is fine. But if you're working in some whole domain that Pink doesn't understand, and you end up having to add every one of your algorithms as a new primitive, then you haven't gained anything.
But just to be clear, who has to vet that extension? Isn't it that young?
Ultimately, it's the poor young woman in the middle, yeah, that has to vet each of those extensions, and that's why we don't want to do it that way ultimately. I'll have a little more to say about that later, but let's, for the moment, move on and talk a little bit about Arabat. Arabat is another differentially private programming language produced a little bit later than Pink. And the idea in Arabat is similar to Pink, but it's a more restricted language. So it gives you less flexibility, but for the programs that you can write in Arabat, it gives you a lot of power. In particular, it gives you the power to run them on clusters of machines in a MapReduce style. So Arabat is differential privacy very specifically applied to MapReduce computations, but then on the system side, engineered in a very comprehensive way so that you can actually run them on huge data sets on large clusters of machines. Moreover, in Arabat, well, let me show you the picture and then we'll see. So the view of the world in MapReduce computation is you have your data set. To get your answer out, you do it in two phases. First, you map a function over your data set that does some local computations, like deciding whether you're interested in this record or not. And then you take the results of the mapping phase and put them through a reduce phase that crunches down and aggregates the information that comes out, like taking a sum. And the insight in Arabat is that it's the reducer that has to be trusted, and where the attention to differential privacy has to be applied, whereas the mapper can be more or less arbitrary. So in Arabat, mappers are written in as arbitrary Java code, whereas reducers are provided by the Arabat system, and there's a fixed small finite number of them, like 6. So this is again kind of similar to pink, that there's sum and count and average and a couple of others, but that set is closed.
So, just to be clear,
Mhm.
The mapper works on, say, the data of one person at a
The,
time.
the mapper works on a record at a time, yes.
And what is the range of outputs that it can produce?
That is, if I remember right, a user-specified parameter in Arabat. So it's going to output basically a real number, but within specified bounds. And if it outputs something outside those bounds, it'll be clipped. And once again, the selection of those bounds. So Arabat is another rather dynamic system. So the selection of those bounds is completely up to the programmer. And Arabat itself gives no help with getting them right.
I guess to expand that question, so is there some notion of stability or sensitivity of what the mapper is doing, or it can do anything and then the reducer will just do that?
Basically, the sensitivity of the mappers is calculated from the bounds of the interval of answers that they're allowed to produce. So it's a very straightforward thing.
It is the length,
It
the
is
range,
the
the
length,
length of the
right.
range.
Yeah, sorry. Yeah, it is exactly the size of the range. Okay. So when I said a minute ago that the mappers can be more or less arbitrary Java, I did mean more or less. So the less part is you have to be a little bit careful about what the mappers are doing. Otherwise, you introduce the possibility of side channels, where mappers can communicate with each other or can communicate with outside parties. So Arabat is pretty careful about this and uses various low-level Java tricks with class loaders and operating system security features that to restrict what mappers can do that may leak information in that way. I'll come back to that point later on as well. So, yeah, excuse me.
Maybe when you're done with our.
Okay, good. So really, the security or the privacy properties of Arabat come from a combination of access control for preventing bad leaks and information channels between mappers and the outside world, plus differential privacy at the level of the reducers. Okay, and then we've already talked about this, the clipping to the range of the mapper. Okay, so any questions about Arabat?
Just a quick question. So, assume the reducer can only output results for keys that actually occur in the data set, but they have to output results for all possible keys?
So I think answering that depends on knowing exactly what the reducer is doing. So if the reducer is doing a count, for example, then the keys aren't really part of the output.
Well, no, so the reducer MapReduce emits one output for each key.
Mm-hmm.
So if a person could come in, who's not currently on the data set, but could come in on a key, a possible key that's not representing the data set, the reducer has to emit a value for them too. So you have to have outputs for the possible key.
So remember, the reducer is not outputting. The reducer is outputting in this setting. Think of it as one real number,
Okay.
not information for each key. So the reducer is always doing aggregation.
So it's not traditional MapReduce.
It is less than traditional MapReduce. Okay, were there other questions to talk
Yeah,
about
I
now?
have a question about how this relates to something like pink, for example. So
they seem to be doing like qualitatively different in the sense that this could have been, you know, implemented in pink. You could have, this lives at some higher level, it feels like, than.
So I think of them as fairly similar, actually. Or rather, I think of Arabat as kind of an instance of pink with a lot of extra engineering particular to the instance that it is.
So, like it seems, okay, it depends on the set of reducers you allow, I suppose,
Right.
but couldn't you just, you know, if you ask people to write their mappers in C#, wouldn't this then be, couldn't this be just sort of run in pink where?
The method could just contact and send the record to website or something like that.
No, but in pink you have this thing where you can say specify the predicate to be that's going to be used to group that's going, you know, you can ask to select all the records that satisfy a given predicate where the predicate is written in C#, right?
Yeah, but
So I'm not sure which aspect we're focusing on now.
Okay, anyway,
There is an access control aspect to pink, which it depends a little bit here whether we're talking about the pink paper or the pink implementation.
I see.
So in the pink paper, Frank described a design for restricting the actions of the mapper components, as it were. That pretty much matches what they do in Arabat and leads to the same protections. In the implementation, he actually didn't finish that part. So what you can write in pink as mappers is really arbitrary C# code, and that's not safe.
It can like publish.
It can publish whatever it wants. It can write things to global variables. Here's a kind of sneaky side channel that in pink mappers can use. They can communicate information using the privacy budget. So a bad mapper in pink can run a subquery that uses up the whole privacy budget, and then that's a globally observable fact. So, but that is clearly not intended in the. That's just a fact about the implementation not being completely finished in that aspect. Other questions? Yes.
I think the main difference in terms of the language model between Pink and Arabat is the join operator. In MapReduce, it's doable, but we have to kind of jump through some hoops.
Mm-hmm.
Pink's supports it very nascently and very nascently. Is in the join operator.
Yeah. So what Ilya said was that Pink's join operator is not easily implementable in Arabat. Okay, thank you for all the questions. Keep them coming.
Wait, one more question.
Yes, please.
Can you just give us a quick overview of what reducers are available?
I could if I remembered exactly, but I should call you back. Okay, so let me talk for a little while then about static analysis techniques, and in particular going back to this issue of how do we know in advance? How do we, in this case, easily construct a proof in advance that only a certain amount of privacy will be used by a program? Okay, so at a high level, Fuzz is a higher order functional language. So Arabat and Pink both live in the object-oriented family of languages. Fuzz lives in the functional family of languages, but that's kind of an inessential aspect. What's more essential is that the type system of Fuzz incorporates sensitivity tracking natively and internalizes the notion of probability distribution so that adding noise becomes not something that you do at the end of a computation and that falls outside of the programming model, but something that we can really talk about internally in the language. And the key property of Fuzz is that every well-typed program of a certain type is differentially private, and that fact is a corollary of the soundness of the type system. So like every programming language with a good static type system, it has a type safety theorem, and that type safety theorem implies differential privacy when you look at the definitions. So the key idea of fuzz is the observation that in order to understand privacy, we need to understand sensitivity of functions. And so if we had a programming language that was able to track sensitivity, we would be most of the way there to having a programming language for privacy. So the way it's going to look is like this. So here's a little query we might write in fuzz. And so the query is at the bottom of the slide. It's a little lambda term that says, tell me a database D. And what I'm going to do to it is first filter D with the predicate over 40, and then ask for the size of that. That is, ask for the count, and then add some noise. And the type of this function on the right-hand side there is going to be that it maps data, that it's a one sensitive function. That's what the lollipop symbol means. So it's a one sensitive function from databases to distributions over the reals. And then in order for this to work, we need some functions, we need some subroutines or primitives up at the top. So over 40 is a predicate that takes rows of the database and returns ordinary Booleans. Size takes databases and returns reals, but notice that the type of size, again, has a lollipop in it. So it's a one sensitive function from databases to reals.
How do you know that? Does it tell you that, or are you telling, where does that symbol come from? Does the programmer specify that, or is the language somehow?
So the definition of the language offers two types of functions. There are arrow functions and lollipop functions. Underneath, they're both functions, so in a sense, lollipop is a more special kind of thing than arrow. They're all arrow functions. Lollipop functions are the one sensitive ones.
I think the question is, are the types given by the programmer, or are they inferred by the compiler? Or are given any?
The types at the top are assumptions that I'm making on this slide that we've provided these things in some way. The type on the bottom is calculated by the compiler. She's looking like that wasn't actually your question.
I thought that size is one symbol. Do I, the programmer, have to know that?
I'm going to define the meaning of the lollipop symbol so that it means that.
She's wondering about a dishonest programmer
Yeah,
who will say
what happens if I don't
size
know?
has lollipop.
So I'm going to have a type checker, which, when I write down a program, is going to look at it and say, according to this set of rules, this program is or isn't of this type.
That's what I'm saying. So size, and basically as a programmer, I'm saying size, and I think size is one stable or one sensitive, and then the programmer will check.
And then the compiler will check. So in this case, so let's look at this. So over 40 is some arbitrary piece of code that we will have written someplace else, and that type will have been checked by the compiler. Size is a primitive. It's provided by the definition of the language. And the fact that it is one sensitive is something that we have to prove separately and believe the proof of in order to believe that the language is good. Filter, similarly, filter can be built out of lower level primitives. So filter is something that you can program up in the language. And the type of filter, the type that the compiler calculates for filter is essentially the compiler's promise to you that it is a one-sensitive function. Add noise is a primitive. Okay, so I'm going to move on in a minute to specific types and the way we define them, and maybe this will be more clear. But I'm glad you're asking questions, because I think this is exactly the point where a programming language person and a person from this audience might have very different ideas about what anything means.
Why does add noise have a lollipop?
Add noise is a one-sensitive function from reals to distributions over reals. So that's what that's how you read the circle. So, and
It's a different notion of sensitivity over distribution.
it's sensitivity over
it's a
distribution. So
it's
so
a
the
metric, right? Everything
exactly. So
comes
the
from
so the
metric.
game that I'm going to play, which I've already started, but I'm going to go through it in more step-by-step fashion, is that in the classic differential privacy world, there are kind of two things that have distance metrics. There are reals and there are databases. In this world, everything has a distance metric. So all of the primitive types come with a defined metric, and all of the type operators, all of the ways of building more structured types from less structured ones, like pairing and building function spaces and building lists and things like that, have ways of are mappings on metrics as well as mappings on types. Okay, we will come to details of that in 1 minute. Other questions for now? Okay, let's go on and get into the details, and then please ask more questions.
So if it's just a notation question.
Yes.
So when I see two words separated by a space, that's applied. The first one's a function being applied to the second.
Yes, yes.
And
Thank you.
I kind of compose from left to right.
Right. So in particular, filter over 40D means apply the filter function to the function over 40 and the database D.
That is, apply the filter function to the function over 40, take that, and apply it to D, right? There's some
You can read it both
implicit
ways.
querying
That's right.
going.
All right. So like every good functional language, this one has currying, but that's inessential
But we're
for
not
today.
all used to reading that way.
Yes.
Anymore.
Yes. Okay, and I've already said this, but the main theorem about the language that makes the language interesting is that if E is a closed program with no free variables, and its type is tau lollipop circle sigma, then E, when you run it, will produce an epsilon differentially private function from random function from tau to sigma.
So where did you get the epsilon from? It doesn't show up in
It's built into the definitions.
it's a fixed.
It's a fixed, it's a globally fixed parameter for this presentation. There are other ways of setting it up.
In here, tau doesn't need to be the type of databases. It can
Tau
be
does not
any
need to be the type of databases. It can be any old type. Typically, we'll be interested ultimately in top-level programs where it is the type of databases. But it makes perfect sense when it isn't, and also when sigma isn't the type of reals.
So lollipop, circle, sigma. Can you explain that?
Yeah, so sigma is some type that I'm not specifying here. Circle sigma is probability distributions over sigma. And tau arrow, or tau lollipop circle sigma, is one sensitive functions that take a tau as an argument and return a distribution over sigmas as a result.
And here the metric on distributions is this sort of multiplicative
Yeah.
log scale thing.
Yeah, so it's going to be a multiplicative log scale metric on distributions. Okay, so yes, please. Epsilon comes out of nowhere. It's built into the definitions are organized such that this theorem holds. So there are, you'll see an epsilon in an appropriate metric definition at a certain point. Other questions? Okay. Let's go on at least one slide. Okay, so as I said, the game we're going to play here is for every type in the whole language, we're going to define a metric. And then we're going to say that a function, an arbitrary function from tau 1 to tau 2 is C-sensitive if it does the appropriate thing to the metrics on tau 1 and tau 2. Okay, so this is just a completely straightforward generalization of the standard sensitivity definition with inserting arbitrary tau1 and tau2 and their metrics. Okay, so
So maybe you're gonna come to this, but when you say it's one stable with respect to distribution over height, I'm not sure I understand what that means.
let me come to it in a few slides and then ask again. Okay, so let's start easy. So the type of reals is going to be the most interesting, one of the couple of most interesting base types in the language. And its metric is the usual one. The other familiar one in this audience is the type of sets. So these are sets over arbitrary tau, so sets of any type you like. And the metric on those sets is the usual Hamming distance. And then along with this primitive type come a number of primitive operations that allow us to do things with that type, either transforming within that type or producing elements of other types like R. So size takes a set to a real number. Notice that it has a lollipop in its type, so it's a one sensitive function from sets to numbers. Filter is analogous to something in pink. Map is analogous to something in pink. So each of these things is given a type that expresses its sensitivity in its arguments. You can do other things, union, intersection, difference. Notice that I'm using a tensor symbol there, a circle cross, which I'll come to defining in a moment. And then split is like pink's partition. Okay, so you can define a collection of useful operators on the primitive type set. Okay, here's a little bit more interesting one. So there are many metrics on the reals. I defined one and chose it. What if I want one of the others? Well, I can take the one that I gave you and scale it by using a type operator called bang. So the type operator bang sub r describes a type whose elements are the same as the underlying type tau, but whose metric is scaled by r. And now a nice fact is that a function is a c-sensitive function from tau1 to tau2 if it's a 1-sensitive function from bang sub c, tau1 to tau2. And that means that we're only going to need one flavor of bang when we come to, one flavor of lollipop when we come to talking about lollipop, because we only need primitively 1-sensitive functions, and then we can construct arbitrary sensitive functions on that basis. Okay, here's another type operator. So given tau1 and tau2, we can form the type of pairs of tau1 and tau2. And the metric on that type is the sum of the distances between the components. So for example, now we can write binary functions because f1 there of xy is actually taking one argument, a pair, and returning the sum of the elements. And f1 is a 1-sensitive function on pairs under the metric that we just gave. Same for subtraction, same for the identity function, for swapping the elements of the pair. An interesting one is the compare and swap operation, which is useful if we have time, which I think we probably won't. I'll show you a sorting algorithm whose basic operation is compare and swap. A non-example is copying. And so given the metric on pairs, copying one element of a pair in the input is a 2-sensitive operation. And the type checker would tell us that. Of course, there are other metrics on pairs. So in particular, instead of taking the sum of the distances between the components, we can take the max of the distances between components. And this gives us a different notion of pair on which different primitives make sense. So, and now for the people with a little bit of programming language background, let me digress a little bit. There's another kind of familiar area of programming languages where there are two different kinds of pairs, and that is linear type systems, or so-called linear logic type systems arising from the branch of logic called linear logic. Linear logic goes back a couple of decades and has been very influential in programming languages because it's a reformulation of logic due to Jean-Yves Girard and others, which pays more careful attention to the use of resources. So in linear logic, if you have an assumption, you can prove something from it, but you can only prove it once. And if you want to prove it twice, you have to copy the assumption, and that's an explicit operation, and you have to pay attention to that. So linear logic is a logic of resource usage, and that has obvious connections that you can imagine to computer science and programming languages. Now, interestingly, in linear logic, as here, there are two kinds of pairs. So there's the tensor pair and there's the ampersand pair, and they have different behavior and different properties. Here, what's interesting about the difference is that with an ampersand pair, the expectation is that you can only use one or the other side of the pair. So the destructor for an ampersand pair is first projection or second projection. And once you've done the first projection or second projection, you've used up the pair. With tensor pairs, the primitive operation is pattern matching, where you get access to both components of the pair. Okay, so we don't have time to go too deeply into that story, but the point is that the 2 points are that we need, in order to write all the programs that we want to write, we need a fairly refined analysis of these metrics, which in some cases gives rise to a multiplicity of metrics on the same space of values that we're familiar with from day-to-day programming. And then second point is that that multiplicity is very familiar from linear logic.
But the way you describe these two, it's a beautiful analogy, but the way you introduce the two end constructors, they only differ by a factor of 2. So it's not like in linear logic where they're significantly different. In your case, they seem to be up to a factor of 2.
I'm not sure what you mean by a factor of 2. So if we have two pairs, each.
One has a
Yeah. Okay. Yes. So I do see what you mean by a factor of 2. Yes. These are the natural operators that we found. If you want to experiment with another one that behaves differently, you're welcome to. And we have a framework for you to check that what you would do with your new kind of pairs kind of plays nicely with the other things that we're providing. Okay. Functions we've already talked about, but here they are. 1 second, let me finish explaining this and then come back to questions. So tau1 lollipop tau2 is the type of one-sensitive functions, and of course it needs a metric. So this is a higher order functional language. We're going to be passing around functions as data, and so we need to know what is the metric on that space as well, and it's just the maximum distance. It's the pointwise distance between the results of the functions. And now, as we said before, we can encode C-sensitive functions. We can also encode arbitrary sensitivity functions if we allow the bang operator to take infinity as a subscript. Okay.
It's not symmetric, right?
It.
symmetric in F and F prime, but not symmetric in tau 1.
Right, it's symmetric in F and F prime, but not tau 1. Okay, moving a little more quickly. Oh, sorry, there was a question. What was it?
So actually, I just wanted to ask, what is the example of the tau1 ampersand tau2? Is there a particular example of type tau1 ampersand tau2?
Let's see. Okay, so the question is, what's a simple example of tau1 ampersand tau2? Let me call you back on that, because I don't have a practical example off the cuff. They do come up. Okay, so we can have disjoint unions, and a natural metric for disjoint unions is that, so if you take the disjoint union of two types, and now you have two elements of the disjoint union, and you want to know how far apart they are. If they come from the different branches, then they're infinitely far apart. If they come from the same branch, then you use the metric for that branch. In particular, this gives us a story about the Booleans, because the Booleans are just the disjoint union of two singleton sets. So in this language, the distance metric on Booleans is that identical Booleans are at distance 0 and different Booleans are at distance infinity. So the consequence for programming is that if you have a Boolean, it's easy to write a C-sensitive function using it for any C you like, but it's very hard, in fact, not possible for a non-trivial function to be into Boolean to be C-sensitive. And that's a reflection, if you want to think of it this way, of the fact that, that functions into Boolean are discontinuous. Okay, skimming a little bit, we can introduce lists or indeed build them from simpler things if you set things up right. And we can write functions like sorting and more interesting functions that would be familiar to you in this notation and check that they have the claimed types. Okay, there's one more little thing, and I'll go through it quickly. So I've talked about the sensitivity aspect of the language. What I haven't talked about is the circle. So let's just talk about it quickly. And what's nice about introducing circle as an explicit type operator in the language is that it allows us to internalize the add noise operation. So rather than the program rather than writing a program that results in a real and then expecting the environment of the program to supply the noise, we can have add noise as an operator in the language. And write programs that perhaps use it many times or put it in a loop or whatever.
But now that's now not symmetric. I mean, do you actually use, because it could be that if you reverse D2 and D1, you get, in one case you get infinity, in the other case you get 0.
Let's see.
So you might want to take the max of this and delta 2 over delta 1?
Yes, absolute value.
It's absolute value.
Oh, okay.
Okay. So I've given you the main ideas, and I think I'm actually going to race through the rest of this. The critical theorem that you prove is called metric reservation, and this is the theorem that connects the operational semantics of the language, the way that programs actually compute, with the privacy guarantees that are embedded in the metrics. Okay, that's it for Fuzz. But let me tell you a little bit about what we're doing now. We're working at Penn on a language called dfuzz. There are several authors listed on the bottom of the slide, and they're all here. So you can find out as much about dfuzz as you want. The motivation for dfuzz is a limitation in the flexibility of fuzz. So the essential problem with fuzz is that it doesn't track data dependencies of sensitivity. So if you look at the untyped part of the language, just the underlying kind of functional computation model, it's very similar to Pink. But the type system restricts what programs can be judged as correct or private. In particular, for example, at the bottom of the slide is written out the type of the k-means algorithm running for 2 iterations. And in that type is the constant 6 epsilon. So this is so if you run the k-means algorithm twice, if you iterate it twice, a 6 shows up in that subscript. If you iterate it 3 times, then a 9 shows up, and so on. Each one of those unrolled loops has a type in fuzz, but the function that decides on the basis of some other piece of data or some property of the database that it calculates dynamically that decides how many iterations to run does not have a type in fuzz. Okay, so the question we want to answer in dfuzz is what would it take to extend the language of types with enough precision that we could track that kind of dependency? And we have a paper coming out in a couple of months. We are working on an implementation. I will tell you that the main hard part of making that implementation work is that the type checker is now generating rather interesting constraints, which will probably take an SMT solver to deal with. We can tell you more about that offline if you like.
Sorry, when does the in kind of vision for dfuzz, when does the checking happen?
It still happens statically. It still happens statically. So I guess the vision would be the monk writes down the program, gives it to the person in the middle. Person in the middle runs the type checker, whose output now is a set of constraints over integers and reals, unfortunately. And now the person in the middle has to submit those constraints to a constraint solver and make sure that they're satisfiable before being convinced that the query is safe to run.
So I guess what I'm wondering about is, take something similar to like the multiplicative weights kind of mechanism that Morris was describing, and that if you wrote a program for it, just looking at it, it might look like it's going to have to do lots of queries and add noise lots of time. But somehow there's a proof done by hand that says actually there's only going to be a small number of these kind of update rounds, and so if you were dynamically checking, you might see, we've only used a small amount of the privacy budget, and it's hard to imagine how statically one would know that.
Indeed. So this is a perfect segue into the last component of the talk, which is machine checking. So, each of the approaches I've described offers a kind of fixed set of primitives, and then ways of combining them. If your algorithm is doing something like this multiplicative weights scheme, where our primitives haven't heard of it, and the reason why it's only this sensitive or has only this impact on privacy is subtle, it's unlikely that you're going to be able to write that program. So that is a limitation of the approach and a challenge to the people working on it. But another way out is to say, well, I don't want a programming language whose primitives embody a particular set of mechanisms. I want the freedom to write down an arbitrary algorithm and an arbitrary proof in full-blown mathematics that algorithm is differentially private. But I still want the person in the middle to be able to check quickly that the proof is correct. Okay, so that gives us not all of the ease of use of the programming language approach, but it does give us the scaling benefit that is the most critical thing. So another kind of thread of work in the programming language community is machine-checked frameworks for differential privacy. And I'm just going to briefly mention 2 of them. One is from IMDEA, and it's called CertiPriv. It's an extension of or an application of an earlier project called CertiCrypt. which was a formalization of a large body of cryptographic reasoning. So it's a COC formalization. COC is a proof assistant that allows machine checking of proofs. So it's a COC formalization from first principles of differential privacy and a compositional method for reasoning about arbitrary programs and their differential privacy. Now, you could imagine, and this is another challenge to people working in the area, you could imagine combining the benefits of these things. You could imagine taking certipriv. In fact, I have a feeling that they're working on this from some things that Gilles has said to me. You could imagine taking certipriv and having a type checker for Fuzz as one of its proof methods, a particularly automated one. But where the correctness of that proof method would have to be established by lower level reasoning in the certipriv framework. That would give you actually a really nice kind of spectrum where when you happen to be writing in the, when your algorithm happens to be expressible in the Fuzz world, you would just write it in Fuzz, it would be type checked automatically, and no further work would be needed. When you were using extra primitives, you could add them to Fuzz and prove their privacy. And that proof would be checked, and the person in the middle would not have to believe you. They would only have to believe their proof checker. Or when you're using a completely different mechanism that just lives outside of that world, you would set all of that aside and prove everything by hand from scratch. Okay, another piece of work in this area, which I want to mention because Anupam is in the audience, is work on extending the notion of differential privacy to interactive systems. I put this in the category of machine check proofs because their long-term aim is making their proofs machine checkable. So, and since I'm almost out of time, I'm going to run right past this, but please talk to Anupam about what they're doing. It's very nice. And then, extremely quickly, I'll mention some other work in programming languages and some other work in systems, just kind of flashing it by you so that you know that it's out there. So there's some beautiful work on continuity of programs by Swarat Chowdhury and his collaborators with very deep connections to differential privacy. There's work on differential privacy in process algebras that extends notions of differential privacy to a concurrent context. And now going to the systems work. There's work that I alluded to a little bit on dealing with covert channels. In particular, the new piece of this work, and again, all of the authors are here, the new piece of this work is dealing with timing channels. So dealing with not quite differentially private programs where the mapper says, if embarrassing fact, then delay 10 seconds, else return immediately. And as you can imagine, that opens a gigantic channel, which is surprisingly hard to deal with. Okay, going quickly past that.
Let's say a few words on how you deal with it.
You deal with it by making sure that all of the mapping steps take exactly the same amount of time. But exactly. And that's the hard part. Okay. Okay, and then one other thing that we're going to hear about more this week is when you implement your differentially private programming language, be very careful about floating point arithmetic. Floating point arithmetic is not the same as real numbers, and we all know that, and occasionally forget it to our cost. So talk to Ilya about that. One other thing that we're going to hear about at the end of the week is differential privacy in a distributed setting where the database itself is spread across multiple sites whose owners don't trust each other. Okay, and then this is the last one. Gupt, another kind of whole system approach to differential privacy, which I will let you talk to its authors about. Let me wind up by saying there are many challenges in the programming languages applied to differential privacy domain. I think you'll be convinced already from the talk that the main challenge is balancing expressiveness and degree of automation. That's the thing that is going to be hard forever. A more practical thing that people are finding hard is bulletproofing implementations. The kind of ongoing work that a lot of people are engaged in is extending the tools and methods that I've described to a broader range of data structures, more interesting things like graphs and streams, and a broader range of mechanisms. But I would like to leave you with, I would say the biggest challenge, or the biggest, at the moment, stumbling block for progress in this area is the lack of demand from real users. So, or the demand may be there, but it doesn't reach us. So the thing that would move us along the most is to have somebody come along and say, I have this really bad problem in differentially private data release, and I need some kind of a programming language or something to help me do it. If we had 6 or 8 of those, that would be fantastic. So if you know any, please come and talk to us. In the meantime, thank you very much.
Let's take maybe a quick question or two, although we had lots.
Well, so I can see where these techniques are useful, but they seem to help primarily the data owner, because it's the data owner's responsibility to make sure that only differentially private programs run. But the analyst, I would argue, really cares about accuracy, utility. And these techniques don't really help them write good programs. They just help them accurate programs. They help them write private programs. And
That's an accurate point.
okay, and I'm glad you agree, and I wonder if there's, I mean, coming from a database point of view, there's a need for an optimizer. So you'd like the user to be able to write logically equivalent expressions of what they want to compute, you know, or a declarative language is I guess kind of what I'm saying.
Yep.
That you can declare what you want, and the system will help you find the right way, the best way to execute it. But I'm understanding you correctly that that theme is not in the work.
That theme has been recognized, but is underexplored.
So there are privacy analysis that use the two norm over vectors in our the norm. And it seems like in your system those would be 2 distinct types.
Mm-hmm.
You can get R squared,
Yep.
get to and get norm. So
Yep.
is that
Mm-hmm. Okay, thank you.